Let's talk about vectors. Almost everything that we need to know about vectors for this semester can be fit on a single page, and we're going to do that now. A textbook will tell you that a vector is a quantity with both a magnitude and a direction. This differentiates it from scalars, which are just an amount. If we went hiking and we hiked for 2 miles, 2 miles would be a scalar. However, if we specified that we hiked 2 miles to the northeast, that's a vector. 2 miles to the northeast, both a quantity with both a magnitude and a direction. We are going to be denoting vectors by putting little arrow hats on them, like I'm doing here. And we're also going to get into the habit of drawing them as right triangles. The reason we do this is because we know a whole lot about right triangles, and we would like to leverage our knowledge in analyzing new physics problems. So we're going to say that every vector has both an x part and a y part, and we are going to specify an angle in reference to either the x or the y axis. Speaking of which, it is very important to keep in mind what your axes are when you're drawing vectors. Customarily, we will put the x direction in the horizontal and the y direction in the vertical. This is not always the case, but this gives us a good baseline. Our goal is going to usually be to take the information we're given about a vector, write it in component form, do math on it, and then convert it into some form that's easy to talk about. So our goal is to write down a arrow hat, which means a vector. We'll use these angle brackets to enclose the components. This is the form that makes it easy to do math on a vector. If we are given the length of the vector and its direction, as we frequently will be with problems, we can use trigonometry to get it into the form that we want. The sine of the angle, as I've drawn it in blue, is going to be equal to the opposite, the y part of the triangle, divided by the hypotenuse, or the length of the vector. Note that we're going to be using these vertical horizontal lines to denote the length of the vector. Simply, we can say that AY is going to equal the length of the vector times sine theta. Similarly, we can draw a relationship between the cosine of the angle and the x part of the triangle. Just because, though, I've written the cosine is going with the x and the sine is going with the y, doesn't mean that will always be the case. For this blue triangle, I've drawn the angle adjacent to the x-axis, and that's the only reason that cosine and x are going together. Be careful denoting which angles you're given in a problem. You don't want to accidentally call sine when we should be calling cosine. If we have the opposite case, and we know the legs of the triangle, but we don't know the angle and we don't know the length, we can use trigonometry to get at that as well. So the tangent of the angle is going to be equal to the y part over the x part, the opposite over the adjacent. Or we can say that the angle itself is going to be the inverse tangent of AY over AX. Lastly, we can use the Pythagorean theorem to get at the length of the vector if we already know the legs. Right? So the length of the hypotenuse is going to be the sum of the squares of the other two sides. So this is how we break down a vector and recombine it. Frequently, we are going to need to add two vectors together. Graphically, this is if we did first the blue vector, hiked 2 miles northeast, and then we hiked, say, 1 mile southeast. So our B leg is in red, our A leg is in blue, and the net distance we've traveled from the very beginning of where we started to where we ended up. I'll draw that in purple. And that vector we're going to call A plus B. Mathematically, dealing with this is actually really simple. If we want A plus B, the sum of two vectors, then the x part of the sum is the sum of the x parts, ax plus bx. And the y part of the sum is the sum of the y parts. Lastly, if we need to multiply or divide a vector by a scalar, say we wanted to do the northeast leg twice, right? If we do 2 miles to the northeast twice, that's the same as multiplying 2 onto our vector. This doesn't take much mathematical effort. We just distribute the constant inside to both of the components and do whatever math we need to do to it. So there we go. Almost everything we need to know about vectors. 6 or 8 weeks from now, we will talk about how to multiply two vectors together. But for now, this is all we need. I'll see you in class.